Welcome to the array visualization and machine learning part of the tutorial. The work is just beginning in these two directions. This is why this part is rather concise. Visualization is crucial for data understanding. As an example, consider Climate Weekends, a free software for fast 3D visualization and analysis. Climate Weekends retrieves data from Kronos Server, a predecessor of Kronos DB. Kronos Server is an example of a system for high-performance data dissemination using custom networking protocols. Currently, R&D in visualization in RadyBMSs falls into three categories: the high-performance data dissemination, the implementation of standard protocols for interoperability, and predictive visualization with the help of ML techniques. All these trends consider both rendering images inside an RadyBMS to avoid costly data movements to external visualization systems or delivering raw data. Having multiple systems, how should they interoperate with each other? That is, how to share or exchange array data in a way that is understandable to different systems. For geospatial data, many protocols have been already developed outside the database community. Hence, RadyBMSs are starting to implement these protocols. Most protocols assume that the server can render data on its side to avoid transferring large data volumes over the network. In addition, standardized file formats have always been the primary containers to communicate between the systems. Kronos DB storage layer uses raw files in standardized file formats that are readily accessible to other software. Rassdaemon delivers arrays of diverse networking protocols. You can visit the Earth Server Playground for a demo. Kronos DB implements a WMTS server and can deliver multidimensional arrays via WMTS. The server is distributed. This enables large array visualization and avoids and minimizes data movements between the cluster nodes. Kronos DB can work in two modes. It can deliver raw data in standardized file formats via WMTS, for example GeoTIFF. Kronos DB can also render images itself and deliver visualizations to thin clients like the OpenLayer map you see on the slide. The forecast system uses machine learning to predict areas of future user interest and to prefetch respective tiles beforehand from SciDB. Forecast keeps the history of tiles visited by the user and learns from their past movements. It also computes diverse machine vision features to compare data tiles for visual similarity. To speed up the visualization, Forecast prefetches data tiles that it feels the user will visit soon. A recent work proposes fast matrix multiplication algorithms that are orders of magnitude faster than Spark-based approaches. Its main idea is to use special chunk shapes for matrix multiplications. It then targets several popular ML techniques like linear regression and PCA. The idea is to split the computation in two phases. The first phase computes a data summarization matrix that later helps to significantly reduce the memory footprint and accelerate further computations. We have also evaluated how matrix multiplication behaves when implemented using native RadyBMS facilities. One of the key observations that a traditional model of push-based or pool-based streaming can have not the performance, which is not as efficient as expected. In these cases, an MPI-like communication capabilities could be highly beneficial for an array DBMS. There are also evaluations of some array DBMSs, for example, SciDB, on linear algebra-based analytics. We did not yet focus on efficient algorithms for array DBMSs related to machine learning. Hence, much to be done to make array DBMSs one of the best choices for ML. However, this is a fresh and important direction, because we would like to do ML efficiently and directly inside an array DBMS to avoid costly data movements. Machine learning and visualization are just paving their ways to array DBMSs. Hence, both directions have endless R&D opportunities. Many novel and exciting innovations in this area are yet to come. Please join and innovate.